Hello, this is Dr. Christy Patton-Lukes, Chemical Engineering Professor at Missouri S&T. In this lesson for process control, we will be looking at Chapter 4, Transfer Functions and State Space Models. Okay, so what we've been doing so far is looking at solving differential equations, and we've done this all using Laplace transforms. Probably have some questions like, why on earth is this the only technique we've done? Okay, well, we've used this technique because it leads us into a place that actually will make things easier. Now, one of the issues is that the point of view of our models is that we are always initially at steady state, and then suddenly at time t=0, a disturbance occurs. Now that means that we always have initial conditions, which means Laplace transforms will work, okay? Taking the Laplace transform of our differential equation isn't really that hard, okay? It's doing the last step, the inverse Laplace transform, that's the hard part. That's where the problems come in. But the thing is honestly, if I can understand what's going on without having to do that last step, things will be easier. So most of the time, we're going to work in the Laplace domain and only occasionally check back with what's going on in the time domain using things like the initial value theorem and final value theorem. Most of the advanced control techniques are based on Laplace domain models, so it is helpful also if we are comfortable working with us. But there are many textbooks out there where they work in the time domain and don't use Laplace transforms. I honestly find that math is more difficult if you will just accept the fact that we're going to move to Laplace land and stay there. Now we will be developing a transfer function for our model. A transfer function is simply a mathematical expression in the Laplace domain that relates our input function to our output function. The way we're going to develop this transfer function begins by defining deviation variables. Now, a deviation variable, something new, right? We haven't talked about before. Basically, what we're going to do is we're going to define a new variable, x prime, that is x minus the steady state value of x. We're going to use an overbar to denote the steady state value. And we'll use a prime to indicate a deviation variable. All right. Now, an advantage of a deviation variable is that if you start at steady state, at time 0, the function will be 0, and any of its derivatives will be 0. That's going to make taking the Laplace transform a lot easier. Okay, so step 1, define deviation variables. Step 2 will introduce a first-order Taylor series approximation. We don't always need to do this, but this step is going to be what we will call linearizing the differential equation. If the differential equation is already linear, we can skip this step. Once we have a linear equation in terms of deviation variables, we'll do any algebraic simplification we need. We'll take the Laplace transform and we'll think about the answer. We're not going to actually take this back to the time domain. We're going to realize very quickly that I can tell a lot about what's going on in the problem by looking at simply the Laplace domain expression. Okay? So I'm going to pause the video here, and we're going to do another example where we'll do an example of developing a transfer function. First, we'll do it for a linear differential equation. Thanks for your time.